Good afternoon, everyone. I'm really happy to be presenting to you today. I wish that we could be in person as we normally are, but the circumstances have necessitated this type of interaction, and it does have its benefits in some ways. I hope that we can start and continue a good discussion. I'm not going to enhance my introduction because the session chair did a great job, but I am Bill Toth. I retired from ORNL a little over a year ago, and I've been continuing to develop the ideas that we'll talk about in this presentation and are also available in the paper. I've joined forces with Rob some time ago, and he'll give his own brief introduction to not only write and present this paper, but to continue this important work. Rob?
Well, hello, everyone. I'm Rob De La Espriella, CEO of DLE Technical Services. And just a little bit about my background to tell you what got me here. First, I spent 6 years in the nuclear Navy, supervising reactors and driving nuclear submarines. I went straight into commercial nuclear for 20 years, most notably a stint with the Nuclear Regulatory Commission. Also, I was on the Deming team that won the Deming Prize from Japan at Florida Power and Light in 1989. My role there was to be a root cause subject matter expert. So my training in the area of complex problem solving goes all the way back to 1988, and I've been an instructor in that area since 1991. After 20 years, I started my own business, began consulting on the Department of Energy campus as a senior policy advisor. And there I helped them solve their most complicated problems at the nuclear weapons complex and the national laboratories. Most recently, and only about the last 5 years, I've been really developing this process for solving the most complex human-centered problems in modern socio-technical work environments. And in the last couple of years, Bill and I have been collaborating to make this an even better and more enhanced process. So with that, we hope you'll enjoy our presentation today. Bill?
Thanks, Rob. Starting out, and foundational to the ideas in this paper and good analysis and design practice that would improve nuclear and radiological security and nuclear material management, is the idea of critical thinking. We can discuss critical thinking in a definition proposed by the Foundation for Critical Thinking. Yes, there is a foundation for critical thinking that will follow. Or we can talk about critical thinking skills as capabilities that analysts and designers must have in order to adequately address complex nuclear security and management issues. To summarize the critical thinking foundation's definition, it is, first of all, the intellectually disciplined process of gathering, organizing, conceptualizing, and synthesizing information generated by observations, experience, reflection, reasoning, and/or communication. The purpose for this is so that we can develop informed opinions instead of uninformed opinions, reach sound conclusions, solve problems, and take the best course of action. It's important to recognize that this definition is wide open to effectively using quantitative and qualitative sources, foundational idea to our paper. As you will see later, we advocate for a structured and rigorous method that uses and integrates both qualitative and quantitative sources for pre-event analysis, design, and mitigation plan development strategies, and post-event root cause analysis and evaluation of the readiness to return to full operation. The organizational theorist and systems thinking pioneer Russell Ackoff proposed this reasonably cynical hierarchy of the constitution of the human mind. It involves data, 40%, information, 30%, knowledge, 20%, understanding, 10%, and wisdom, sadly, none. Ackoff considered wisdom at the top of the hierarchy, but I've flipped the order in order to make this important point. With the development of more and more powerful computing resources, we continue to favor data and data-driven solutions above all other. Ackoff created this hierarchy several decades ago. I think that we continue to move in the direction and become hubristic about the problems we can solve with the prominence of artificial intelligence supported by incredible computing power. I've included a picture of ORNL's Frontier computer, which has made the publication Top 500 as the world's fastest. Many take this position that with enough data and enough computing power, we can solve any problem. I don't personally agree with that. And for certain types of problem, this combination of data and incredible computing power, the achievement is nothing short of miraculous. In practice, however, with human-centric problems as they pertain to our nuclear and radiological material security and management, this data computing power combination is not as useful. We can debate this point. So to highlight the point, there is no automatic process that converts data into wisdom in Akoff's terminology. Technology encourages a focus on data and promotes a kind of hubris that crunching vast amounts of data with powerful enough machines can solve any problem. Analysts making these assumptions will inevitably miss the mark and propose wrong solutions to complex problems. This diagram is a representation of a typology from Alford and Head entitled Wicked and Less Wicked Problems. They have proposed this quadrant where the x-axis represents increasing difficulty of solving problems and the y-axis represents increasing complexity. Clearly, when difficulty and complexity are low, we have easy, simple problems. We can characterize these as tame, as indicated. As both systems complexity and problem-solving difficulty increases, however, we began to move into complex problems, and beyond that, we approach what C. West Churchman and Horst Rittel described as wicked problems. The term wicked doesn't mean resistance, it means resistance to solution. It's not synonymous with evil. The hope for solving problems is challenged because they define them as sometimes impossible to fix because of incomplete, contradictory, or changing requirements. When we think about international efforts for nuclear and radiological material security with the myriad stakeholders, organizations, motivations, territorial boundaries, transportation routes, we can see how many problems can approach wicked, but we intend to try to solve them, of course. A couple of notes on definitions. Complicated is a word that has as its root something that means folded, so that if we simply unfold the problem, we could understand it better and possibly solve it. Complex has a different root, and its root is a word that translates into plate, which is more like a weaving together of components. Unfolding won't help. We have to approach it in a different way. The image that comes to my mind when I think about this interweaving is a bowl of spaghetti. Each strand represents a systemic component, a relationship, a communication channel, or an operational process. Whatever your unit of analysis inside your project scope. In proactive, preempted design work as analysts, we need to see these individual strands and analyze their characteristics individually, looking for their inherent strengths and deficiencies. After understanding these characteristics independent of interwoven or coupled systems, we need to then understand the interactions, the relationships, and other characteristics. It's been my experience that system deficiencies are often found at these points of intersection. These are not simple two-dimensional overlay type interactions. They are complex 3 or even 4-dimensional puzzles that are very difficult to understand.
And I wanted to add here, Bill, in terms of post-event applications, where we do formal root cause analysis, we also have grown to understand that complex problems are not caused by a single root cause. It is a jumbled mix of root causes and significant contributing factors. And there again is your picture of a bowl of spaghetti, a bowl of causal factors that we have to now unravel and hopefully be able to display clearly on our causal analysis chart. And that's the kind of work that Bill and I have been doing for the last few years.
When we talk about qualitative research methods or qualitative sources of information, we're talking about at least the items on this list, but the field's pretty broad, and we should include any sources that bring clarity to the problem that we're trying to solve. I'd like to focus in particular on the last item on this list, which is narrative collection and interpretation. Of course, this collection can be done in the context of structured or semi-structured interview settings, so there are overlaps with these methods. I have had great success collecting the actual experiences of specialists in the field who have invaluable insights into the operations of nuclear and radiological facilities. Their contribution moves design teams quickly to identify the best mitigation plan solutions. This is in contrast to taking those same individuals and having them fill out a Likert scale type evaluation of their experience, which would essentially reduce their pages of rich experience down to a single number. My experience was 5. And what does that even mean? The irony is that this Likert scale number is a distillation of more rich experiential narrative, which is often used as quantitative data. It wasn't born quantitative, we converted it. What we're proposing to unravel the strands of the complex systems, analyze them, and determine their interactions is a process that we're calling hyper-integrated causal analysis. This methodology was born in root cause analysis work, hence the name, but as we continue to develop it, we see that its application in pre-event analysis and design work. The major constituents are as described. Critical thinking is foundational to the work, as we're incorporating an integration of many sources. Systems awareness is a term that I prefer over systems thinking. The fact that we're dealing with multiple complex systems pertaining to nuclear and radiological security is beyond debate. So we don't need a special discipline of thinking. We simply need to be aware of the many interacting systems. The quality of our solutions is directly related to how we consider these multiple systems. Analysis of defenses is critical. We have either designed defenses such as barriers, physical protection systems, regulations, cultural norms, but we also have what I'm describing as impromptu barriers, such as an aware and well-trained staff who will alert when something's going wrong. It's important to look for deficiencies in these defenses because oftentimes the bad thing happens when the holes in the defenses line up and allow the bad thing to happen. We're interested in behavioral factors on an individual level, such as malevolent actors, insider or outsider, or cultural aspects that would blind an organization to the development of suboptimal practice. The quantifiable data is accommodated in the model. And then finally, to introduce one new term, we think of these systems as socio-technical, which further emphasizes the combination of human factors and technical elements. The following chart represents a practical application. The small text on this chart is not meant to be readable. We simply offer this as an illustration of the structure. Please focus only on the callouts. First of all, the entire chart has as its foundation critical thinking skills or critical thinking in general. This is the portal into which we accommodate quantitative data and qualitative data. And that comes in many forms and many of the things that we talked about previously in this presentation. This highlight is for the analysis of defenses section. This is when we delineate the defenses and look at them individually to see how effective they are. In this section, we talk about behavioral analysis and at-risk behaviors, error-likely situations. And overall, each one of these columns represents the different systems that we're actually analyzing with our socio-technical systems approach. In conclusion, complex problems have causes that are in the interactions of multiple system dynamics. They have to be unwoven, like that bowl of spaghetti we were talking about. In complex, regulated, operating, and manufacturing environments, significant issues are rarely, if ever, caused by one root cause. We're looking for multiple problems on many levels. Traditional approaches have favored quantitative research methods for the solutions to these complex problems. We also need to look at qualitative approaches when analyzing these complex problems. Rob?
And fourth but not least, to solve these kind of problems required a very structured and rigorous methodology that can actually accommodate any kind of data analysis, but also unravel the complex human-centric interactions in our modern socio-technical work environments. In that case, we have a great chance of identifying the defenses that aren't working very well in terms of the design phase, or also the defenses that didn't actually prevent an event in the post-event root cause analysis. In either case, when we have good solutions, we can actually have a chance of preventing their recurrence, or getting out in front of these issues before an event even takes place. Thanks very much. That concludes our presentation. Right, Bill?
It does. Thank you for your attention, and we look forward to the further discussion.